So in order to derive the weak form of the boundary value problem, the trick is you're going to multiply both sides of this equation with a test function and then integrate it using iteration by parts. So the first thing we need to do is to pick a test function. So let Vx be a test function. So what is a test function? It is just a function, any function that is in the same space like the analytical solution U. So do you still remember in the previous chapter, we mentioned that U, well, first of all, U has to be a continuous function. And also, what else? The first derivative of U and the second derivative of U, they are all continuous function. So it means that U is in the C2, right, function space. Furthermore, in this case, you need to satisfy the homogeneous Dirichlet boundary condition. So that's why we need this subscript D for the function space. Remember, U is a function of X. So we need to write down what is the domain of X. In this case, X go from 0 to L. So this is what we write. So U belong to the function space C2D from 0 to L. Okay, so we want Vx to be in the same function space. Okay, as I mentioned earlier, what we're going to do is we multiply the test function to both sides of the equation. So let's write that down. The next thing we're going to do is we're going to integrate both sides from 0 to L. Okay, so we're going to put an integral on both sides. So remember, when you introduce an integral, you need to put the differential of x at the end, right? Okay, so now let's use integration by parts to figure out what this integral equal to. So what should we do? Well, do you guys remember the table that I mentioned in class, right? The first column, we pick out the term that we want to take derivative. For the second column, we pick out the term that we want to do antiderivative. So look at this integral here. Which term should we put on the column that we want to take derivative? Well, obviously, you want to choose Vx. The reason is you want to save this term, the term with the derivative, for antiderivative column, isn't it? Because when you take antiderivative of the derivative, you will make the derivative disappear. Imagine if you put this term on the derivative side. So when you take derivative again, you have to deal with the second derivative. So that makes the integral become more complicated. Okay, so let's say if we take derivative of v, what do we have? We have v prime, right? We can also write dv dx, right? Either way, either notation is fine. Yeah. So on this side, what is antiderivative of the derivative of this product? Well, antiderivative derivative make the derivative disappear, isn't it? So all you have is the product inside. Okay. And the next thing that we're going to do is we're going to combine these terms together. So this is what I'm going to do, right? Remember, we have the cross arrow first, and in this case, we're going to have the horizontal arrow down here because the derivative here doesn't hit 0, right? So we still need this horizontal arrow. After that, I'm going to put the sign. Remember, we have to alternate the sign. Yeah. Okay. So now let me rewrite this integral using iteration by parts. So how does it look like? So remember, we still have the negative there. So let me put a negative there in front. Yeah. And inside here, we're going to take Vx, right, times this term. And for the term on the horizontal line here, we're going to write an integral for those terms, isn't it? Okay, so this will be an integral from where to where? From 0 to L of, you can write either like dv dx or v prime x. Let me just write dv dx for now. Yeah, and I multiply with kx times du dx. Okay, and you shouldn't forget the dx at the end. Okay, so this is what happened on the left side, right, of the equation. Now on the right side, you cannot really do anything with this integral. So let's go ahead and just leave it as it is. Okay. Now let's take a look at what we just wrote here. Remember that we're going to evaluate the first term here, right, as 0 and then at L. So let's go ahead and plug in L. So what do we have? And don't forget to distribute a sign also. So negative, yeah, VL times KL times du dx at L, yeah, plus, remember we bring the minus in, right? So minus with minus would be plus. So here we evaluate this term as 0. Okay. And this minus with minus here will give me a plus. So I have a positive integral from 0 to L dv dx times kx times du dx. Right? And again, we can do anything with the right hand side. So let's just copy that integral as it is. So let's take a look at these two terms here. Do you remember that the test function has to be on the same space like u, right? In this case, what it means is v as 0 is equal to v at L and equal to 0, isn't it? So it means that the first term will go away as well as the second term. Okay? So now all I have is, what do I have here? All I have on the left hand side is this integral, and on the right hand side is this integral. So let me write down integral from 0 to L of kx times du dx times dv dx, right, equal to the integral on the right hand side, which is the integral of fx times vx dx. Okay, so this is called a weak form or the variational form. Okay, so you can see how easy it is to derive the weak form of the original boundary value problem.